Good morning, my friends. Hey, there's a cat in class today. I like it. Outstanding. Sharing the screen. That worked. It's a miracle. How is everyone? Thumbs up, says Jesse. I got to go kayaking yesterday, so I'm happy, man. It was rather cold, as you might imagine, but I did not swim, so it was good. Well, I just got rolling this morning, and I just barely started grading quizzes. So as soon as I get off, I'll work on grading those. So I'll have those back to you today sometime. They're just going to be sitting in my open math, I assume. Actually, I don't know. If any from last term, do you get some kind of an indication that they're in there, or do you just go look and they're there or they're not there? Actually, don't really know what it looks like on your end.
I've usually just checked myself because I don't think I've gotten any notifications that's been updated.
I think that actually makes sense. Too many notifications is a little bit annoying. But anyway, I'll have it done before today's over so that if there's anything that you want to discuss, you'll have time in class tomorrow. My intention tomorrow, because tomorrow's review is just you have a review that's sitting in my open math for you right now, and between whatever homework questions, primarily though the review, whatever things pertain to the review, just because that's where the majority of your me telling you what you need to know for the test is going to be. And then, substitution is just one of the techniques that we've looked at since we started this section. So it's not going to, take over the whole test. But of all the things we've done so far, it's I don't know if I want to say it's the most important, but it's the first time we can actually take an integral of something that isn't, I don't know if I want to say obvious, but it's not just the power rule in reverse. So you're definitely going to see at least a couple of good solid questions on that. So like I said, in some respects, I don't have anything else I need to show you, but what we need to do is just kind of get better at pulling this off and going really slow, going systematic, substituting every single thing out, kind of making sure all the X's go away and U's show up, and then, see what the result is from there. So I am just going to take questions that are similar to what is in your book. I think I made a copy of a page out of your book. I might just steal some of the questions out of that. Let's just start off kind of with this classic example. Let's see. Let's even be a little bit more organized and say 5.5 substitution. So sometimes in your assignment too, like you might see, like you're used to seeing the dx sitting out here sort of being multiplied by it. And it is actually being multiplied because remember, that's the width of your rectangle. And the equation is the height of your rectangle. Those are kind of the y values. So don't forget that's all this is really saying. Again, if you want to walk away with kind of a conceptual understanding of this. So let's see. Sometimes because it's multiplied, you might even see in your assignment like the dx is sitting up here, which to me is kind of, I don't know, dumb. Like, why not put it out there where it's not really part of the problem. You're not really doing anything with it anyway. But I want to, don't write this down because I think I want to make this a little bit more interesting. let's make that a cubed, and I don't know, I'll put like a 2x up here. But this problem is not going to work. And I'm purposely doing that so that you kind of see a pattern that you're going to see in almost every question that's sitting in your assignment. In other words, the skill I'm showing you here, the technique to switch this into some other form, is really narrow. Like it's a very well defined, or it's canned. Like the problems have to be made up very carefully. If you just make up something random, it isn't going to work well. What I'd like you to understand today ultimately is this is really integrations. Maybe I should say response, or even just nothing. One of the tricks to getting good at like what do I substitute here is to think that really substitution is the response that integration has to the chain rule. The chain rule was junk inside of junk. And when we saw that with derivatives, we said, ooh, I gotta pay attention to that. And the same thing is true here, because notice you have the square root of junk. In other words, the square root of something complicated. And so the garden variety thing to do is to say, wow, that square root of ugly, I wish that mess would go away. And so the classic substitution then is to say, I think I'll let, again, I'm going to pick a different letter this time just so you don't get too used to U. V equals, well, what's under that square root sign? Because that's going to clean things up. Does it make sense that takes the chain rule away if I do that? Because now I just have the square root of V down on the bottom. And so now it's not junk inside of junk. It's just one equation. It's just the square root. That's one of the things you kind of look for. You look to take something complicated and make it simpler with substitution. Now let me show you what I mean by that's not going to work. So let's see. If that's what V is, then I also am going to need dx to go away. So let's figure out something for dx. So in order to do that, I'm going to have to take a derivative. So as I said yesterday, the thing that makes the most sense is just to take the derivative of both sides. So the derivative of V is the derivative of V, because we don't know what it is. We don't know, are we taking the derivative with respect to X or with respect to W? I'm sort of just saying, I don't know, I'm not even going to decide. So I'm just going to say the derivative of V is the derivative of V. And the derivative of 1 is 0. And the derivative of 4 times x cubed would be 12 times x squared times the derivative of x. That's the chain rule right there happening. So great. And since I have a dx on top, maybe I'll finish this by solving for dx. And so that means that's dv over negative 12 x squared. So in a sense, I've solved it for dx, but notice I still have this x here, like that didn't completely work. So that's not so good. In a sense, I'm not done. I mean, you really need that to be dx equals and a bunch of v's on the other side. So how am I going to get rid of that x squared? That's really a problem here. Is it possible to solve this for x squared? The answer is, well, maybe. It seems like it's going to be awful ugly. It might be the case. But I'll tell you what would be really nice, and I'm going to go back and actually change this right now to be the canned questions that you're going to see in your assignment. What would be really nice is if this original problem just miraculously had not 2x, but 2x squared sitting up there. Do you see why that would be wonderful? Well, I'll show you why. Basically because as a result of that 12x squared being down there, it's actually going to cancel with that x squared on top. And so usually I had to kind of get rid of, okay, I got rid of that x is now gone, it's a v, and then I just got rid of this dx, and now I got to get rid of this other x. But this is going to get rid of it for me. That's kind of what I'm saying. So let me show you what I mean. So I don't know, let's stick with red. So let's see, what do I have now? So I've got the integral of, I'm just leaving that 2x squared up there, and it's over the square root of v. And then I've got dx, but dx was this dv over negative 12x squared. Aha. Now do you see it? So the x's are just going to cancel out. So it turns out, and you'll see this in, as I said, so many of the questions in your assignment, and I might even flip over to my Up in Math and show you this before we're done today. But this is a very well-designed problem for substitution. And what I mean is, and what I said about it being very narrow is if I took that squared away, I'm not sure, but I want to say this problem is not possible, or at least is not easily possible. I might have to do a second substitution. Like I got it into V's, and then I might have to say, okay, well, I can't do that, but maybe I could do it again and I'll switch it into U's. You could actually do this more than one step and maybe eventually get it right, which again, I think is pushing the limit of what we're trying to accomplish here. We're ultimately not trying to just be able to take the integral of everything. We're trying just to learn how to think of this as an idea, a process that can accomplish something. So if what's sitting down here has its derivative in the problem somewhere, that's what you're going to see today a ton. Like if this was a cosine down here, but the derivative of cosine is sine, and there was a sine up there, that's going to be great. And that's what you're going to see today. So we got a lot of problems to do, so let's just continue for now. So let's see, that means, awesome, this and this can cancel. Would you agree now, mission accomplished? I have all V's, and so, yes, that's mission accomplished. Now again, notice this is an indefinite integral. There's no limits of integration to this problem. So if this was a problem in an assignment, I have no choice but to take the integral and substitute V back out of the problem. And we'll do examples of both kinds. And so, okay, let's see, that cancels, and the 12 cancels. 2 over 12 is negative 1/6. And so I'm even going to write the negative 1/6 out front. And all I have then is, do you understand why I'm writing it this way? Everybody okay with the algebra there and why I'm doing that? Why did I write it that way? Why didn't I just write it as 1 over v to the 1/2, or write it as 1 over the square root of v? Why did I write it this way? Somebody tell us.
It's easier to deal with when it's factored as such.
Yeah, this is going to be a power rule question. So I want it written as a power, so I can add 1 and divide by the power. And it's nice if it's on top, if it's not a fraction. I don't want it to be 1 over v to the 1/2, then it still looks like quotient rule. But written like this, now I got it down to where it's power rule. So sure enough, the original question I couldn't do, but this question, now that I substitute it, now I can do it. And the 1/6 just comes along for the ride. That's why I said, oh, I'll just stick it outside and ignore it for later. You don't have to stick it outside. You can just leave it in there. It's fine. It doesn't really matter where it is. So I say, okay, cool. I add 1 to v to the negative 1/2, which makes it v to the 1/2. I divide by 1/2, and then I still have my negative 1/6 out here. What's wrong with what I just wrote?
You just took the integral and you put the integral sign.
Yeah, don't put the integral sign. You already did it. You did the integral. Don't put it in there. You might know what you mean, and if you get it right, I'm just going to sit there grading and trying to decide what to do with it. But again, just get in the habit of doing this correctly. Really, that's your answer now. You have 1/6 there. And dividing by 1/2 is the same as multiplying by 2. 2 times this 1/6 is 2/6 or 1/3. And so I think I got negative 1/3 square root of v for this. And then I just hearken back to my conversion, throw the x back in, because there never were any v's in this problem. Throw the x back in, and I'm done.
How did you find dv?
I'm sorry?
How did you find dv?
Because I said, in order to create a dv, I've got to take take the derivative of that statement to create DVs, to create derivatives effectively. From last term, if you have an equation that says how V and X are related to each other, in other words, if I know X is 7, this is an equation that tells me what V is. If I know X is 2, I know what V is. If V is 8, I know how to figure out what X is. But in derivative land, we're saying, yeah, it's great, but what I want to know is how they're changing. How fast are things changing? How fast is it actually going? That's why I take a derivative. So I said, okay, what's the derivative of V? I just took the derivative of both sides. Derivative of V is the derivative of V. Again, sometimes you can just write it as V prime. As I said the other day, you could have done it this way too. Take the derivative. Well, you could take the derivative with respect to X. What's the derivative of V with respect to X? You could write it that way. The derivative of 1 is 0, and then the derivative of 4x cubed with respect to X is negative 12x squared. These two processes are exactly the same. Do you see they're the same? Wait. Sorry, I actually wrote this all wrong. Didn't I? No, I didn't. I'm fine. So in the end, what I wanted to know was, what's that dx? Like, I got to get rid of that too. I need everything to be v's. If I decide I'm going to switch this into v land and try to make that easier for myself, then I need to get rid of dx as well. And if I need dx, then that means I'm going to have derivatives. And so I had to take the derivative of my v's and x equation. And that's what created it. So then I solved it for dx. Either one of these two methods, this solved for x, or over here, if I solve this for x, I'd be multiplying by dx up to this side and then dividing by negative 12x squared. I'd have the same answer I had over here. Now I got something to substitute out dx for. So I replaced this dx with what dx is now equal to, dv over negative 12x squared. Did I say enough about that? Did I answer your question? Please keep asking. If I don't, just because I talked doesn't mean I answered your question.
Yes.
Okay. So then all I got to do to finish this is put x back. So it's negative 1/3, not the square root of v, but the square root of what v is equal to, which is 1 minus 4x cubed. And then technically you put a plus c on the end of it. What I noticed in my open math that I just looked at right before class today is, I'm kind of thankful for this. I think that's kind of nice. The plus c is actually outside of your answer box, like they put it in there for you. And you just have to kind of write in the business end of it. So again, that c is kind of a technicality.
Shouldn't it be x to the third instead of the second?
You are correct. One must be able to read one's own handwriting. Thank you. So let me ask you a question. Like, what did I just find? I found a brand new equation from the original equation. What is this equation? I mean, you could say it's the integral, but what is it? What does it do? What's it for? Do you understand what you're doing?
You can plug in your limits to this to find the area under the curve from one point to another.
Exactly.
A derivative shows you how much or how fast things are changing. The integral shows you how much things have changed.
Yep, those are both true. Visually, it's finding the area under the curve. And what Vail said is also true. If the original problem was a rate of change, then this is actually going to tell you how far you actually went. So remember, this is just an area finding equation. Again, I find it personally a little unsatisfying when I'm given an indefinite integral problem where there are no limits of integration sitting here. I find it a little unsatisfying. I'm not really overly sure that I didn't make a mistake here. And so I think it was Alacia that rescued me from stupidly writing x squared there. But does it make sense I would have caught it had I checked my work, had I went back to the original equation and graphed that and looked at the curve? And because of the fact that you're dividing by something, there is going to be holes in this curve. So I could say, all right, I'm going to evaluate it from 3 to 2. And then I would have put my 3 and 2 in down here and I wouldn't have got the same answer. And then I would have went hunting and found my mistake. But just don't forget what it is.
What to set v equal to? Like, why didn't you include the square root, or why didn't you do the 2x? whatever it was on top.
Yeah,
2x squared.
in a sense, I just got lucky because when I wrote it in here, when I replaced dx with dv over negative 12x squared, I just noticed, hey, look at that. That x squared cancels with x squared, which means I didn't even have to deal with it. Made my life easier. Do you see logic in that? That's why you got to be very
So you just
algebraic.
So you just chose. Wait, I'm confused. So you just chose it randomly, or?
No, this problem was very canned. We got extremely lucky. In other words, this 4x cubed, when I took its derivative, produced a negative 12x squared. And the fact that there's an x squared down here, and miraculously the problem had an x squared on top, meant that those were able to cancel out. Had that not been the case, if there was just a 2x up there, does it make sense those would not have canceled out? And I would have had to continue because the x's would not be gone yet. I mean, basically got to keep at this until there's no more v's anymore. And in this case, because the problem was canned, I got really lucky and then they dropped out. Again, I'm going to do more examples. You're going to see this before we're done today.
Hey, Doug, I was just thinking about before you had the two, like what Martin was pointing out. Are you not able to manipulate the equation over there once you've turned to v? So if you wanted to say, like, square that, so 2x, it would end up being 4x squared. And then the v would just, the square root would cancel out under the v. So you just have v.
Let's see, are you able to square that? You got to be careful with the fraction. Like if you have a fraction, I'm not sure if this is what you're saying yet, but if you square top and bottom of that, those aren't equal. So you can square both sides of an equal sign, but you can't square the top and the bottom of a fraction. If you do that, they're not equal anymore.
Oh, shoot. Okay.
Thank you for pointing that out. So yeah, there's a lot of algebra to this, if you will. You're going to make algebra mistakes, both accidental ones and also important ones that you need to learn something from. So in this case, I'm done. I found the error of finding equation. I just didn't have to use it for anything. Fine. Let's do another one kind of like that one. I'm stealing questions out of the book here. This is question 48, if you happen to care. Do you see this as the same problem as last time? What I would like to do, my knee-jerk reaction to this question is, I would like to let u be equal to what's in the parenthesis. Now, there's all kinds of other things I could try. Would you agree? I might also want to let u be the whole thing, like x squared plus 1 squared. Maybe that's a good idea. Or maybe u is just the x squared. Do you agree those are all possibilities? But generally speaking, if I pick the one I originally picked, that's going to make the bottom nice and simple. So they might all work. I'm not really sure. But I don't want to make it look like what you pick for a substitution is really simple. Do you notice the derivative of that statement just magically happens to be sitting up on top? And right now you don't notice it, or you don't think about it much. But if that wasn't up there, if this was just a 2, we're going to be in trouble. Like, we're not going to be able to do this question. It's going to be hard, like hard for me, hard. I'm really going to have to think. But because the derivative of the statement that we're substituting is sitting there in the problem, this question is going to be easy, just like the last one. So, if you will, that kind of takes care of that. Now, I just want to move on, and sort of my second consideration is, what am I going to do with this with this dx over here. I need that gone too. I'm sort of trying to get rid of x's, trying to get everything, well, substitute everything out. How am I going to get dx's? Well, the only way I get dx's is if I take the derivative of an equation that's got x's in them. The only equation I got is the one I made that transfers between these two worlds. My u equals x squared plus 1. So I take its derivative. Again, the easiest way to do that, I'll write it a little different from last term. The derivative of u is the derivative of u prime. The derivative of junk squared is 2 times the junk times the derivative of the junk. Isn't that chain rule? Again, I could see why you might think it was just 2x, but it's just that I did not choose to take the derivative with respect to x. I just said, I'm just going to take the derivative of both sides. The reason why that language is u prime and x prime is not so great is, notice those look like ones. It looks like u to the first power. So that's why they're written du and dx a lot of times. And the derivative of 1 is 0. So more commonly, you might see it written like this. And again, I'm trying to get rid of dx, so I want to solve this for dx. So I can substitute it out. And I would, of course, do that by dividing both sides by 2x. So I've got kind of that ingredient. And now I've got this ingredient. And again, I'm not super happy that there's an x still sitting there. Like, I wish that wasn't there. Can I get rid of that x? Sure. Can't you solve this for x? So I would subtract 1 and take the square root. So x equals u minus 1. Does it make sense that's really ugly? But if you will, that's a third ingredient. So now I have kind of 3 ingredients. I can get rid of anything I want to get rid of now. Well, let's just go put all that in and see what we got. So I've got a 2x on top. And I've got u squared on the bottom. And I've got dx, which is equal to du over 2x. Does it make sense that I, if you will, didn't even need to do that this time? Because look what happened down here. This x canceled with that x. And by the way, so did that 2 with that 2. Hey, that just made my problem really easy. I didn't even have to use. And frankly, if I had stuck that in there, if I had replaced that x on the top up here, if I had replaced that x like I was tempted to do with the square root of x square root of u minus 1, I might not have noticed it. However, wouldn't I have done the same thing down here? I would have had square root of u minus 1, square root of u minus 1, and I could have canceled them out. So this problem is very canned again. I see in the original problem, the thing that I'm trying to substitute, its derivative is sitting up here. Awesome. That's going to make my life really easy. Great. Now, this is a definite integral. So you got 2 choices now. You can take the derivative of u, get the answer, and then put x back. And then since this original problem had x equals 2 and x equals 0 in it, those are x's, then I could put the 2 and the 0 in for x. Or I could just say, no, I think I'm going to just go into u world and I'll just stay there. That's what we learned yesterday. It doesn't really make any difference. So if x is 2, and I put 2 into that, 2 squared is 4 plus 1 is 5, then I could put a 5 there. When x is 2, u is 5. When x is 0, u is 1. So I could actually just stay in this world if I wanted to, but you can't use 2 and 0 because those are x's. So I think I'm sitting here with a much easier problem to do than the original problem. But again, as I pointed out yesterday, I want to go over to Desmos and just kind of check and make sure these two areas are actually equal, because I just did a whole bunch of algebra and it'd be really easy to screw up. And so I want to see if these two areas are actually equal. Is this area, which I can cheat to get, is it actually the same exact area as the one I just got? Let's go look. So the original problem was from 2 to 0. This is still sitting here from yesterday, so I don't have to remake it again. I'm very happy about that. And the problem was 2x divided by the square root of x squared plus 1, not the square root. X squared plus 1 squared. So that area from 2 to 0 is apparently 0.8 by cheating. So I sort of know the answer I'm supposed to get now. I'm supposed to get 0.8. If I don't get 0.8, then I did all my calculus wrong or my algebra wrong. But what I'm wondering is, if I go from 5 to 1 for the gx equation, my second equation though was really simple, right? It was just 1 over u squared, or u to the negative 2. Oh, good. They both say 0.8. Does it make sense that I know I didn't screw up now? But again, visually, this is really interesting. If I turn the other graph on, under the blue graph, I wish I could color this in. Let me think about this for a second. So let me try something here. I just want to play for a second. Pardon me. I know I can say I want this graph to exist from zero to 2. I know I can do that. So I chopped it off. That's kind of a little more sophisticated trick than just putting a vertical line in there. So the area under that curve. What I'm wondering is, do you know how to shade? Can I actually go in and say that? No, it didn't like that. I thought maybe it would say all the y values less and it would actually let me do that, but it didn't let me do that. So I'm pretty sure there is a way to shade in this. I just haven't figured out what it is yet. So the area under that blue curve is actually the same as the area under the green curve. This is kind of just neat to look at. So I want to go in and simplify this one as well, just so that you can see it. So from 1 to 5. Really? This is kind of neat. I mean, and let's see, can I stretch this out? I forgot how to do this. I think there's a way I can just grab it, but notice both graphs live between 1 and 0. So if I go into the wrench up at the top in settings, and I say I'd like my y values to live between a y minimum of 0 and a y max of 1. See how that stretched the scale of it so that I can see it now a little bit? So what's kind of neat about this is, notice those two areas don't look, the graphs are totally different graphs. And yet the area under the green graph, which is from 5 to 1, is the same as the area under the blue graph from 2 to 0. Isn't that kind of cool? So it's not that the graphs match up at all. They're two completely different graphs. So it's just kind of neat. Let's see, I might as well throw that in the notes. So snap a picture of it. Is this any better sideways? Wow, I forgot to turn my laptop sideways, iPad sideways. That was a mistake today. The question is, are you seeing it? I mean, does this visualization help you to kind of make sure you understand not just how to do this, step 1, step 2, step 3, step 4. That's why people don't learn math, or their math knowledge doesn't persist, because all they do is memorize steps, which works great for one day. But what about next week when you learn another set of steps and another set of steps, and now 6 months goes by? Like, you got to learn how to understand what you're doing, not just how to do it, but what you're doing. So I just changed this into a different curve, yet the area under the new curve is the same as the area under the original, because I did not choke getting rid of all the X's and replacing them with U's. Go ahead.
I'm confused why we changed our limits from 0 to 5 to 1.
Why did we change those limits? Because I am in sort of U land here. And if I want to stay, and I think I understand your question, Eve, did I have to do that? Did I have to change those limits to 5 to 1? No, it just made my life a little easier. Let's finish this problem and see if we can actually, now that we know the answer is 0.8, we're hoping we get 0.8. So notice U to the -2 is a classic power rule problem. What's this person doing wrong? That's a super easy mistake to make. There's the integral. What's wrong?
They're adding -1 instead of +1.
Yeah. Be careful. When it's negative, you're going to screw this up. When you add 1 to -2, it becomes -1. And the power rule says you got to divide by that. Now, you need to evaluate that from 5 to 1. Now, it would look a little nicer if I put -1 and U on the bottom. I think I'm going to have more success looking at it that way. Do you understand that that's okay? If I move it to the bottom, U to the -1, it moves down there as U to the +1. And since it's U to the +1, I really even need the 1. And -1 is just there to tell me what sign the answer is. So it doesn't matter where I put it. I could have a 1 on top and still have a -1 on the bottom. That's fine too. So I stick 5 into that and I get -1/5. I always subtract. I put 1 in it and I get -1. So it's -1/5 minus -1, -1/5 plus 1. Ah, that's 0.8, 4/5. Awesome. Now, I think your question, Eve, was not so much like, why is it 5 and 1, but why did I even do that? Does it make sense that I could have chosen to, once I got the integral as 1 over -u, since u was x squared plus 1, I think this is what Eve is asking. Could I have gone back to x's and then evaluated them as x's? Is that okay? Was that your question, Eve, ultimately?
Yeah, I think I was just confused on why you chose the numbers 5 and 1. Like, where did they even come
Okay,
from?
good. Your question was from here. In other words, this original x was x equals 2. And so if I want to go into U land, well, this is how I convert. So if I put x is 2 in there, 2 squared is 4 plus 1 is 5. So that 2 in U land is going to have to be a 5. That's where I get the 5.
Oh, okay.
And this 0, x is 0 was my lower limit. X is 0, put it in here. 0 squared is 0 plus 1 is 1. So that's got to be a 1. So that's why that's a 5 and 1. Now, I think that saved me a little time just to stay in U land. That's what I would have done. But if you want to do this, do you notice it produces the same answer? In other words, I put the X back and then I was just able to use my X's from 2 to 0. Well, notice you get the same answer. And notice the math is even the same. You put 2 in down here, 2 squared plus 1 is 5. Like you get, that's where the 5 came from in the first place. And when you put 0 down there, you get 1. So either way, you get 4/5. So because of technology, you should never get these questions wrong and not know it. And if they're really complicated, and I can, you know, we're doing, you're just learning substitution right now. We're gonna see this again with trigonometry later on, and there are problems that are really hard in this world. Like you might have to make 2 substitutions and even come up with a brilliant substitution. Right now, I'm trying to teach you how to come up with kind of the easy substitutions. And the algebra can be really complicated. And so you can completely screw this up. And so you want to check it to kind of make sure, did it work? And so what I graphed there in Desmos tells me good. I successfully converted from X's to U's because I got the same answer either way. So I know I didn't blow it this far. Do you understand what I mean about this problem being canned nice? Because the statement down here that I'm letting you be equal to, its derivative just happens to be sitting up there. Does that concept make sense to you? So what I'm going to do,
How come you ignored the squared with the x squared plus 1?
I didn't. Good, thanks for asking. I didn't, because I replaced this with u and it's squared. That's why that u is squared right there.
Okay.
Now I could have multiplied that out, which is probably why your first thought was I ignored it. I could have decided to multiply x plus 1 squared out and, you know, got this big expression. But that actually would have made my life worse, not better. Remember, we don't like plus signs on the bottom.
But we can almost just pick and choose what's going to make our life easier with the substitution.
Exactly. But you got to practice this way more to actually, you know what's actually going to be easier. But I just want you to understand you have options. There's all kinds of things you can substitute. Now, to teach you at least give you a shot, you are not going to see this question in your assignment. What question? All I'm going to do is go back and erase that X. Would you agree that looks easier?
At first glance, it looks easier.
Looks easier. It's like simpler, right? But remember what happened back here. What happened back here was this X canceled with this X, and now that's not going to happen. So I'm making this up because I just want to illustrate how powerful it is that the fact that there's an X squared down there, there's not an X on top. Now, let me show you an example of what you'd see in the book, and then I'll go back in just a second and fix it. If this was an X to the 5th, what's the book problem going to have for you sitting on top up there?
X to the
Yeah, some version of X to the 4th. It doesn't really matter what the constant is. It could be like 7 X to the 4th. That's what you're going to see in your book assignment. It's very nice when the derivative of the thing you're substituting is sitting there. That's what I'm saying. It is not in this case. So let's try kind of the same approach. I'll go fast because we just did this a second ago. U is x squared plus 1. du is equal to 2x dx. And so I'm sitting here then with 2 over u squared. That's really good, right? I'm really happy with that. But dx is equal to du over 2x. So are we stuck? What's my next move?
Substitute the solve for x and substitute the x into u's.
Right. So that x didn't cancel, fine, but can't we use this for a third purpose? Solve it for x, which we did a while ago. Subtract 1 from both sides, u minus 1, and then square root. So then I can replace that as well. So would you agree that I've now landed here? 2 over u squared times du over 2 square root of x, I'm sorry, u minus 1. And if I switched out the limits, this goes from 5 to 1, just like it did before. As I said yesterday, mission accomplished. I won't take the time to do this. But if you, on your graphing calculator Desmos, you went in and you typed this green expression in and cheated and said, what is the area under that curve? And then you went to this pink graph and did the same thing, you'd get the same area, meaning mission accomplished, like I got it. So what's so hard about this?
It's like solving a puzzle, but it's not really defined. It could be done multiple different ways.
Would you agree you have this? What's wrong with that?
How do we take the antiderivative of such a complex equation? Because if we saw this equation originally, we say substitute, but now we're just substituting and substituting.
Exactly.
To what end?
Does it make sense you still can't do that? Again, you might be tempted to, try some things. It doesn't mean we can't do this question. It just means we can't do it yet. Like we're going to have to substitute again. I actually find myself not wanting to quit. Like I actually was just going to show you this to show you like this is not good. Do we have to quit? We can't do this because do you agree it's junk times junk? Like this still looks like product rule. And it's also junk divided by junk. It looks like quotient rule. I can't just do this now. I did not get myself into a place like we did a minute ago. When we got to mission accomplished a second ago right here, we went, sweet. There's only one term. That's just power rule. I'm done. Awesome. Today's assignment, that's what's going to happen every time because you're just learning this. But because I want to teach you how to think, we still can't do that. Does it mean it can't be done? I don't know. What would you try next?
I would try substituting like v equals square root u minus 1.
Yeah, would you agree we got a couple of choices? So let's not quit. I was actually planning on quitting right here, but all of a sudden now I don't want to. One choice would be to notice I've used X's and U's and now I got to try something else like I'll use W. You said, I think that was Connor. Anybody have any other ideas? That'd be good because now that seems pretty simple. I like that. That's got potential. What else could we try?
Could you move make the exponents negative to move them up to the top
Yes.
of the equation and then try to do some algebraic work there?
Yep. Absolutely. So that's also worth trying. In the line of substitution, would you agree that might be good too? Maybe you don't include the square root with what you check?
In your history of doing this, have you noticed that it's better not to include the square root? Just like as a rule of thumb?
That's a great question. Not necessarily, unfortunately, is the answer. Again, it's a question of my attitude is like, if I can get it to work, I don't care. Like if it's a little harder, who cares? Like I actually got it to work.
Yeah, it just seems like every problem we've been doing, you've kind of jumped towards not grabbing it. And I was wondering if there's a reason.
Yeah, well, I don't know. Let's try it. Let's try it. So I genuinely don't know. And do you understand Alicia just proposed sort of a third option here, which is these are multiplied. So can't that u squared come up here as a u to the -2? I'm actually going to go ahead and write that down. U to the -2. And then this other one would be u minus 1 to the -1/2, right? Unfortunately, you can't put those together because we'd love to be able to put them together because then there's not a multiplication sign, which is kind of, again, product rule. So there's sort of three possibilities. And I really actually don't have a great feel for which one to try, but let's try this one since that was the first one proposed. And I want to give you a second. Can you convert this? We converted from X into U. Can you convert from U to W? And the second question will be, was this actually good? Did we find our way out of the woods here? Or is there not a way? I'm just going to give you 1 minute to I'm catching up to you. So let's see, that would mean dw equals 1/2 u minus 1 to the -1/2. Ooh, this is terrifying. Times the derivative of u. Ooh. But that isn't as bad as it looks because that'd be dw divided by 1/2 u minus 1 to the -1/2. And just to clean that up a little bit, wouldn't that -1/2 allow this to move to the top? And dividing by 1/2, remember I screwed this up yesterday, is multiplying by 2. So I actually have dw times 2 times the square root of u minus 1 is equal to du. My u's look like w's, I gotta be careful.
That doesn't seem like that was at all helpful.
Doesn't seem like it was what?
Helpful because we substituted the square root u minus 1 to get it back again, basically.
Yeah, something.
That's on the numerator, right?
So I'm just trying to build my ingredients. Again, the important thing here is just to learn how not to screw this up. I need rid of all these u's. And so I found a way to get rid of this. That was my original choice. I found a way to get rid of that. Now I need u squared to go away. So I'm going to resolve w. So if I square both sides, w would be equal to u minus 1. So that means u equals w squared minus 1. And since I'm trying to get u squared, I'll just point that out as well. And u squared then would be equal to w squared minus 1 squared. So would you agree this is kind of all my ingredients or all my substitutions? I have everything I need now to get rid of everything that I see up there in pink.
When I set my w when I solved my square root of u minus 1 for u, I ended up with u equals w squared plus 1.
Yeah, it is plus 1. Everybody see that? That was a dumb mistake on my part because right here, I'm squaring both sides. That says u minus 1. I'd have to add 1 to the other side, right, to get rid of it. So that should be plus 1. Again, if I'm by myself, I catch that because I'm graphing all this. Okay, so I think I have everything I need. Let's go rebuild yet our third integral, and hopefully this one will be easier. So I'm gonna continue with the same idea. In other words, I'm gonna put in u is 5, because I'm also gonna get rid of those. So 5 minus 1 is 4, the square root of 4 is 2. 1, when I put 1 into this for u, 1 minus 1 is 0, the square root of 0 is 0. Well, that's weird. It's like, it's the same ones we had before. I wonder what's gonna happen. So let's see, what else do I have? Well, I have a 1 on top, and then I have u squared, which is w squared plus 1 squared. And then I have the square root of u minus 1, which is actually just w, so that's kind of nice. And then I have finally du, which is 2 dw times the square root of u minus 1, but the square root of u minus 1 is w, isn't it? I didn't think to note that before. What do you notice about this answer? Maybe you'll notice it now. This w cancels with that w. That's good. Now, what do you notice about it?
We are right back where we started.
We just got back where we started from again. That wasn't helpful. All right. This is what real substitution looks like. So everything we did there is right, but it just didn't help. So I just actually went in a circle. I didn't notice it. Now, what I am going to do is stop here and propose that you keep playing with this for extra credit. And maybe you do go back and try w equals u minus 1, not the square root, because that didn't work, right? Maybe you try that. Now, I want to warn you, I did not practice this ahead. You very well may not be able to do this question, and that's one of the things I want you to understand right now. Substitution is very much an art form. It's art. Like, you have to get the feel of it. You have to practice enough. And I've taught calculus at least 15 times, and I'm not sure about this question right now. So I'm pretty good at substitution, is what I'm saying, and I'm not sure about this. I don't know if that's going to work or not. I want to also warn you, there's some really brilliant substitutions that we'll come back to in chapter 8 that involve trig. Just as a for instance, if I let w be equal to tangent of theta, does that sound like something totally crazy? Like, why would I do that? Well, remember, tangent squared plus 1 is equal to secant squared. I think it's plus 1. And what we don't like about this problem is the fact that there's a plus sign on the bottom. And so sometimes you can make trig substitutions that just seem totally to come from left field. But because tangent squared plus 1, which is 2 terms, tangent squared plus 1, suddenly becomes just secant squared, which is 1 term, that actually could be a way out of the woods here. So the substitutions can get really brilliant. So all I want to do is just open the door to the fact that substitution is really a cool trick, and it's really hard. But do you see what I mean? Why the very fact that that X was missing on the top right there makes this problem really difficult. So the book and I have to be very careful to give you problems that work with substitution, because substitution doesn't always work, and it might even take more than one step. So I hope you see that as cool. But I don't know, try that. By the way, I will give you extra credit if you, even if this doesn't work, like just convert it into W's and then go into Desmos and, graph it and make sure the answer is still, well, I was going to say 0.8, but we don't know the answer to this is 0.8, right? We didn't try it. Just make sure it's still true. Like go to Desmos and see what the answer to this green one is. And then try it with your blue one. Make sure you get the same answer. Again, that is mission accomplished, but I just want you to understand in a little deeper sense that just because you got it from W into U doesn't mean you're done. That problem was not easier. You actually made it worse. I actually made it worse. It was less doable than it was before. Again, in the language of my stupid illustration from yesterday, you just took your UFC fighter that was 6 foot and now they're 7'2". Let's get back on the bus.
I did it on purpose so I could sweep the legs, Doug.
Yes. A reference to Miyagi. Yes, sensei. Take a look at this. Do you see this problem is canned? Again, I'm stealing this as question 57 out of the book. I'll write that in a second. This problem, do you see chain rule here? Because in the denominator, you have sine, which is one function, but then it's also squared. You have a function inside of a function. That's a classic example of when you would use substitution. Remember, we have another method coming later on in another chapter. So, the big picture is you're staring at a question and you have 2 or 3 rules and you're not sure which one to use. Right now, you only have one tool. So you're going to just pound it with a hammer because that's the only tool you got. If I took this cosine away up here and put a 1 up there, this problem is suddenly really hard, really hard. But the fact that there's a cosine up here, this problem is totally easy. Why? Well, because the derivative of what's down below is up there. Isn't the derivative of sine cosine? Remember that sine squared written in that way really means this. And so we're always trying to let u be equal to the inner function, because I don't mind if it's sine of u or u squared. I just mind if it's both. So since sine is the inner function, just like in the previous problem, the square root of junk was the inner portion of it. That's kind of what we're after here. So the smart thing here, the first thing you would try, if you will, is to let u be equal to what's inside of that, which would be sine of x. So there's my first ingredient, which means already I can say this is u squared on the bottom now instead of the sine of x squared, right? That's progress. That's better. I don't mind that. But I still have this dx to get rid of. So how do I get dx's? I take the derivative. The derivative of both sides. Take the derivative of both sides. The derivative of u is the derivative of u. The derivative of sine of junk is cosine of junk times the derivative of the junk. Notice that's chain rule. So if I solve this for dx, then I'd have du over the cosine of x. That's my second one. Do you see that we can quit here? We have everything we need because those cosines are going to cancel. Maybe you see that. Normally, you'd have to say, okay, I've gotten rid of this sine of x, I've gotten rid of that dx, and now I've got to get rid of cosine of x. Let's go ahead and practice that. You don't actually need to do this in this case if you're seeing it, but who knows their algebra well enough to tell me how you're going to get cosine of x out of that? You don't have any cosines. How are you supposed to solve for cosine of x? Remember, sine squared plus cosine squared is equal to 1.
Don't you take the derivative of dx? Like you take the derivative of that equation because then the sine x goes to cosine of x?
I did that here.
And of X,
Just to make sure you see this, because I'm afraid I'm theorizing a little too much. Does it make sense if I think, okay, what do I have so far? I can replace this sine of x squared with, well, now u squared. On the top, I still have that cosine up there. I'm not very happy about that because that's cosine of x and I don't want x's or I don't want u's. But if I plug dx in now, which is du over the cosine of x, do you see it now? Oh, miraculous, gone. Now I don't even have to do anything with that cosine. So does it make sense I didn't even need to do this last step in this case? That's because this is a kind of a canned question. These problems are really easy if the derivative of what substitution that you make, u equals the sine of x, if the derivative of that is sitting up there, beautiful things happen and you have a lot less work to do. If I switch out that cosine and make it tangent, this problem is super hard. If I put 3x up there, super hard. But if cosine is up there, totally easy. So I can solve this for cosine of x by subtracting sine of x. So cosine of x, if I subtracted sine squared from both sides and then square rooted it, does it make sense to you? I'm going to erase this, but that would have been a mistake to put that up here. It's not that it's not true. It's just that, well, it's ugly. And remember, you do know that u is equal to sine of x. And so does it make sense you could have even gone one step further down here and said cosine of x is equal to the square root of 1 minus u squared? But do you see how I might not have noticed how simple this problem gets? Because again, when I stare at my creation here, first of all, this cosine wouldn't have canceled out unless I was smart enough to notice, hey, I can replace this with the square root of 1 minus u squared as well, and so that they end up canceling out. So my point is, I didn't even need to do this. I didn't even need to solve that. I could have stopped kind of clear back here and said, oh, great, those cancel out. Awesome. So this problem just becomes the integral of, again, I could leave it as 1 over u squared. Be careful, just because that canceled out doesn't mean it's now u squared. You understand that? That's common for people to do. That u squared's on the bottom. It's got to stay on the bottom. It's either 1 over u squared or u to the negative 2 because you moved it to the top. Some of you are saying some things in the chat about trig sheet. I'll post that. Did I post that in my open math already? I'll post it in my open math for you. We're going to need that at some point, so I will post that. What's wrong with this statement? Like I'm mostly there, but what's wrong with this? Well, nothing is wrong with it. But I am going to go back and kind of do this problem completely. In the book, this problem started out with this being a definite integral, and it was from pi over 2 to pi over 4. I'm guessing because this is a book problem, that's going to be really nice. If that's true, then as I said, you cannot just put pi over 4 and pi over 2 down here, right? You got to substitute it. So if x is pi over 2, what's the sine of pi over 2? You should be able to reason that out for yourself. Pi over 2 lands here. Sine is what coordinate of that ordered pair? That's the ordered pair. X is 0, y is 1. Sine of that is which one?
It's the y
Sine of the
coordinate.
y coordinate.
It's y. So the sine of pi over 2 is 1. Pi over 4 lands me right here. That's harder. I find myself wanting to have that trig sheet that some of you are just referencing in the chat now because I was like, oh crap, I don't remember what it is. I want to say it's square root of 2 over 2, but I don't know.
It is.
Is it? So look on your trig sheet to cheat or rebuild it all from scratch. So square root of 2 over 2. So I successfully got this into U-land. And not only that, it's now easy or doable. I can actually do it, unlike the last problem. Great, this is simple. Add 1 to that, we already had a problem like this. Add 1 to that, it becomes u to the -1, divide by -1. So that'd be the same as -1 over u, and now I got to evaluate that at 1 and the square root of 2 over 2. So when I evaluate that at 1, I get -1, and it's always minus. And then I put the square root of 2 over 2 in it. I'm afraid I'm going to screw this up, so I'm going to write it out a little more slowly. So that'd be the same as -1 plus, since I'm dividing fractions, 1 divided by the square root of 2 over 2, that'd be 1 times 2 over the square root of 2. So there. If you had to simplify that expression, remember, we don't like square roots to be on the bottom in the denominator. So if you had to rewrite that, I hope you can. But again, I just did a lot of math there. Like you've seen me make all kinds of silly mistakes. Like I'm very unconfident that I have not blown it. So I want to go back into, in the interest of time, I'm not going to, but I want to go back into the Desmos and type that expression in my calculator and see what the answer is. And then it's going to be a decimal, and obviously a decimal that I don't recognize. And then I want to type that into my calculator and see if they're the same decimal. And if they are, then I'm going to box this and say, good job, I got it right. But I'm not confident at all, personally, that I didn't make some math mistake someplace. All I got to do is lose a negative sign or whatever. So at the risk of being stupid, I'm going to box it as though I got it right. But I am going to check it before I post this in case I did get something wrong. None of you have said anything. That's the one advantage I have, is usually when I do something stupid, one of you sees it and points it out. Let's squeeze one more in. I won't hold you over today, but I don't know what example we're on. I want to say 5, but I saw a problem in your assignment that had logarithm in it. This problem looks hard. This is number 66. This is weird. They said the limits of integration are from e squared to 1. That's kind of weird. I'd rather it say 5 to 1. I wonder why they said that. Well, the problem is the natural log of, well, they use the letters p. Let's just stick with p. dp. Huh. That looks hard. Now, what you should think when you see that is quotient rule. You should see something divided by something. That is not good, because remember, we're going backwards of the quotient rule. Like, we cannot do this. This cannot be a fraction. If it's a fraction, I'm in deep trouble. In the last problem, we started with a fraction. We're in deep trouble. But by the time we converted it, no fraction, no problem. What substitution should we try here? I don't really see a whole lot of options, do you? I mean, it isn't going to do anything to do that. Do you understand that? All that's going to do is just rewrite the problem with p instead of, or u instead of p. So I only feel like I have one choice. Do you know what choice do I have?
LNP.
Yeah, in a sense, that's good. I can't think of any other choices. I mean, I guess maybe I could try the whole thing, let u be the whole thing, but then maybe I'm back where I started from again. I don't know, but at least this is easier to try first. So this doesn't feel like it's going to work, but this came from the book. I did not make this up randomly. If I make this up randomly, then maybe this isn't going to work. But this came from the book, and I'm just learning this, and so that there's no way this isn't going to work. But I can't see it. So let's continue. There's sort of our first conversion. That means I'm already on my way. I already have u on top. So at least there's no logarithm, whatever. I also got to get rid of dp. So that's kind of always our second thing we've got to do. So we take the derivative to create some dp's. So the derivative of u is the derivative of u. Who remembers what the derivative of natural log of junk is? What's the derivative
1
of
over
natural
x.
log of junk? Yeah, 1
One
over
o-
the junk. Derivative of natural log of junk is 1 over the junk times the derivative of the junk. So that means dp then, if I multiply p to the other side, is equal to p times du. There's kind of my second ingredient. Well, let's see where we are now. Where am I now? I have the integral of u over p, and then I just found out that dp is equal to p times du. Ah, notice I don't even have to continue. Those two cancel. Awesome. Oh, the integral is just u du. Oh, that's totally easy now. Now, in hindsight, natural log of p is sitting there, and its derivative, 1 over p, is also sitting there. It's actually the same pattern that we saw in other problems. It's just not that easy to see here. If that was a p squared, we're in deep trouble. If the p was up on top, p times the natural log of p, we're in trouble. This problem is very canned. It worked out just nicely because some nerd made it for me. So this is actually just u times du. That's a super easy power rule problem. But remember, we got to keep going because this was from e squared to 1. So how's your brain? Can you do that in your head? Test yourself a little bit. Now you could type this in your calculator if you wimp out, but let's do you know your properties of logarithms well enough to get this exactly right? What's the natural log of e squared? Well, natural log of e squared. What's true about that too? Because this is logarithm.
It can come down to the front.
Comes down to the front. And what's the natural log of e?
They cancel
1.
each other, don't they?
1. Talk about it after class if you're like, I can't remember. Maybe I remember that, but I don't know why. If you haven't, those why questions, even if they're algebra, ask me and we'll talk about them after class. So that's actually 2. The other one is the natural log of 1. What's the natural log of 1?
0.
0. Again, maybe you just have that memorized, but if you want to know, like, why is that? Why is the natural log of e 1? And why is the natural log of 1 0? I don't remember why. I can't build that for myself. There. We just completely changed into u land, and now this problem is super easy. So I say, okay, I add 1 to the exponent, divide by that. The integral has been taken. There's no integral sign. I evaluate that at 2, evaluate that at 0. So I get 2 squared, which is 4 divided by 2, minus 0 divided by 2. I think the answer is 2. I think the answer is 2. It's almost hard to believe. Like, what? That ridiculous statement up there, the area under that curve is equal to 2. I'm going to quickly go graph that in Desmos, and let's just see if that's actually right, since it doesn't take us that long to do it. Let's see. I think I've been saving myself a lot of trouble by not getting rid of things here. So I'm going to say this is, Desmos knows what E is. It thinks of E as a number, not a letter. So I can go here and type e to 1. But what is my x equation? Well, let's even narrow the graph since we can. The graph only exists from e squared to 1, so let's make it do that. And our equation was natural log of p on the top, but in the interest of time, I'll just say natural log of x. It must be in functions over here. Natural log, natural log, natural log. Oh, I think I can just type it. Yeah, there it is. I think I can just type ln, so that was a waste of time. And on the bottom, it was just p, or in my case, x. Huh, it's 2. Sweet, I didn't get it wrong. It's a miracle. What does that look like? Let's turn the graph on and see. That's kind of cool. Isn't that weird that the area, again, please don't forget to be amazed by this. That area under that curve is perfectly 2 square centimeters, if you will. Exactly 2. Do you see why they were trying to be nice to us by making the limits of integration e squared to 1? If they'd made it 5 to 1, I would have thought, oh, great. But then I would have got natural log of 5 and I would have had some crazy decimal. So they're actually just trying to make my life easier in a sense. But I did have to know something about logarithms to pull that off. I don't care if you get your calculator out and type natural log of e squared in, and it says the answer to that is 2, and you say, oh, okay, it's 2. It's okay to cheat on that. But if you want to learn your stuff, you can do better than that. So now I know I'm right. I didn't make any math mistakes. Every problem in your assignment is going to kind of have that feel to it. Stuff's going to drop out a lot more because they were so careful. But what I want you to do is notice, whew, that's sure good that they stuck that in there. Man, that would have really caused me problems if it wasn't all set up so nice. Amazing. Questions, thoughts, anything before? Feel free to leave. I'm always going to go 5 minutes over, so always feel free to just disappear. But anything else you want to say? You don't need to stay, but I think I'll quickly open up my open math and just kind of stare at all the problems with you if you're still here. I guess I would just like to know, can you see the canned nature of every one of these questions? What do you see down here on the bottom? X to the 5th. What is just miraculously sitting up on top? Oh, the derivative of x to the 5th. That's very nice. If that had said 5x to the 3rd, you'd be in a world of hurt. Anything but x to the 4th, you're in a world of hurt here. Sign of junk. The derivative of e to the 5x is just magically sitting out front. You don't notice that when you're doing this problem, but if it wasn't for that, this problem would be very difficult. Junk squared. Sine of x. Look, the derivative of sine x just happens to be sitting there. X to the 5th. Oh, look, x to the 4th happens to be sitting out there. X to the 5th. Oh, look, x to the 4th happens to be sitting out there. X squared. The derivative of x squared is x. Oh, that's pretty awesome. Every single one of these questions has got the derivative sitting out in front of it. X cubed. Look, there's x squared. This is the one exception right here. Notice there's an x out front. You'll be able to get rid of that though too. It's not going to go away on its own this time, but you can still get rid of it in the way that we've kind of practiced. And so I guess I just want you to see that we're just getting started with this stuff. That's really straightforward right now. Most of these questions are definite integrals. Notice this one says from e to the 20 to 1, and they just want an answer. But notice down here, there's no limits of integration. See how there's a little plus c at the end of it? Like they stuck it on there so you don't have to type that part in yourself, which I think is kind of cool. So roughly half of these plus c, plus c, plus c, those are indefinite integrals. Roughly half of them, you don't actually have to check them. But again, I would encourage you to do that. Prepare yourself for the test on Thursday. Just because this one, don't just type the equation in there and submit it. Now you have 3 tries, so if you get it wrong, that allows you to, know you got it wrong, then you can go check it. But do it yourself. Graph this thing, and then notice on this graph, because it's a fraction, that there's going to be a discontinuity in it. Like pick limits of integration that make sense, cheat, get the answer, and then plug those answers into your answer. Make sure they produce the same area so that you know that you're right. Grow in your confidence and in your ability to make sense of what you're doing. It also helps you to just pound into your head the fact that this equation that you get when you take an integral is an area finder. That's what you just did. In the last class, 251, you found a slope finder. Your equation, we called the derivative, was a slope finder. An integral is an area finder. So it's not that complicated. All right, get yourselves on out of here or stay after. I will see you tomorrow for review. You'll get the most out of that review if you spend time with it tonight.
Thank you.
Thank you.